So, why do we need to worry about, or when do we need to worry about second order nonlinearity, or why is this problematic? So, so let us say, let me ask you a question. So, let us say one has an amplifier, right. So, again this is weakly nonlinear, right, and so somebody argues that, well, if I put in an input f here. So, let us say I put in a cos 2 pi f t, and the output obviously contains distortion, second harmonic. So, he says, why do not I put a filter here which will remove the second harmonic. So, let us say the signal bandwidth is limited to b, right, and that is your band of interest. And so, the person says, why do you worry about nonlinearity, right? Let this be as nonlinear as it wants, right. I am just going to simply put a filter and remove the higher order harmonics, right. If I put an input tone less than b, the second harmonic will be around 2b. So, I am going to remove, I am going to have a filter anyway. So, I am going to remove the I am going to remove the second harmonic, right. So, if I just put this whole thing in a black box and give it to you, well, you put in a tone at f and the output looks clean, right. But unfortunately, that is yeah, of course, for input b by 2 for a low frequency there will be a problem, right. But another important issue is what happens when you have two tones cos 2 pi f1 t and cos 2 pi f2 t, right. So, you have two, in other words, the input basically is a two tone input, both have amplitudes A and the frequencies are f1 and f2. So, this is Vi. So, what will V out be? Well, it will be A times Vi, which is A times that quantity, which I am not going to write down again, plus A1 times Vi, sorry, plus A2 times Vi square, which basically will be, I am going to remove A as a common factor, A square times cos square 2 pi f1 t plus cos square 2 pi f2 t plus 2 cos 2 pi f1 t cos 2 pi f2 t, right, which is A1 Vi plus A2 A square times A2 by 2 times 1 plus cos 4 pi f1 t plus 1 plus cos 4 pi f2 t plus 2 cos A cos B is nothing but cos of A plus B, that is 2 pi f1 plus f2 into t minus cos of A plus B plus cos of A minus B plus 2 cos of 2 pi f1 minus f2 into t, right. So, this therefore is if you take out all these terms, it is basically A2 A square, a DC offset, and that makes sense, right, because even though we have seen why it makes sense that you have a DC offset, plus A1 A cos 2 pi f1 t plus A1 A cos 2 pi f2 t plus A2 A square by 2 times cos 4 pi f1 t plus cos 4 pi f2 t, correct, plus so A2 A square times cos 2 pi f1 plus f2 times t plus A2 A square cos 2 pi f1 minus f2 times t. All right. So, let us go term by term and see if it makes sense. Well, this is DC offset. We have seen why this makes sense, right. These are of course the linear terms, and we know obviously why these make sense, right. What are these terms? Yeah, that the second harmonic of the two terms, right. So, if you have the input, well, the output as a component at f1, at f2, there A1A, there is a DC offset which is A2 A square, there is a tone at this is this is 2f1, this is 2f2, and the amplitude. So, this is V out is in red. So, that is basically A2 A square by 2 A square by 2, right, and we also have f1 plus f2. Where would that be? Yeah, if f1 and f2 are close, well, if
either in between the f1 or f1 or more than
yeah,
that.
so if let's say representatively, let's say that this is f1 plus f2, this is yeah A2 A square. Okay, and these are I mean, of course, these are second harmonics of the two input tones. So, we understand where they are coming from, and these two tones, there is one at f1 plus f2 and there is one with f1 minus f2. So, this is f1 minus f2 is going to be f2 minus f1, and this must be A2 A square. Sorry, we kept A2 A square. A2 A square, right. So, what do these represent actually? Yeah. So, what is happening is that the V square, remember, the root cause for all these tones is the Vi square term, where the input is getting multiplied with itself, right. So, of course, when F1 gets multiplied with itself, you get 2 F1, we understand that. When F2 gets multiplied with itself, you get, say, 2 F2, but what also happens is that F1 cross mixes or multiplies with F2, and you will therefore, when F1 multiplies with F2, you will get both the sum and the difference frequencies, and this is what this is often what is called intermodulation. Distortion, right, and because this is coming because due to second order nonlinearity, this is what is called second order intermodulation distortion. Okay. So, most of the time it turns out that for example, in a scenario like this, right, which do you think is more problematic? Which of these two intermodulation distortion tones are more problematic? Yeah. So, for example, if F1 and F2 are close by, then the F1 plus F2 term will be a very high frequency and can often be removed by filtering. So, usually it turns out that this F1 minus F2 tone can be problematic, and so the problem okay, and there is no way of getting rid of this by using a filter, right. So, many times, I mean, so one, remember that the second harmonic, so it is often referred to as the just like how HD2 refers to the ratio of the second harmonic distortion to the fundamental, IM2, which is the second order intermodulation distortion, right, is basically yeah, it is basically the ratio of, yeah, it is the ratio of it is A2 A square by A1A, which is the amplitude of the intermod tone to amplitude of the fundamental. Right, and again in dB 20 log A2A by A1 in dB. Does it make sense? So, every 1 dB increase in the input will cause a 1 dB increase in the IM2. So, so often a way of measuring how linear the amplifier is to plot the input amplitude on a log scale and plot the output amplitude also on a log scale. Right, of both the on the y axis you can plot, I mean, you just show the output amplitude. It can refer to the fundamental, it can refer to the second order intermod and so on. So, if you have an input amplitude which is basically varied in a log fashion, the output will also vary log fashion. So, if you plot the fundamental, right, it is of course linear, but what is the slope?
It is 20 log A1. Slope is A1.
No. The fundamental output amplitude is nothing but A1 times A, right. When you take the logarithm, what happens?
20 log.
Multiplication of
Like 20 log A1 will come slope.
that is not the slope. You are plotting log A versus the output amplitude. The output amplitude is A1 times A. So, when you take the log, this simply becomes 20 log A plus whatever plus 20 log capital A, right, and on the x axis it is 20 log A. So, you will get a straight line with a slope of
Slope is 1 only.
slope is 1, right. Yeah. So, the intercept will basically depend on the DC gain, right. Yeah. So, this is the slope is the slope is 1 dB per dB. All right. Now, what comment can we make about the intermod tone? The strength of the intermod tone will basically be
A2 A square is the
A2 A square, and with what slope will it go up? As you keep increasing the input amplitude, what will happen? Yeah, the IM2, I mean the second order intermodulation tone strength is proportional to A square. So, it will go up with a slope of 2 dB for every dB increase in the input. So, let us I think I should plot this maybe a little higher. So, let us do this. Right, and this goes up by right. So, this slope is this slope is 1 dB per dB and this is 2 dB per dB. So, this is nothing but the second order IM tone, right, and this for a given amplitude, this difference is the IM2 in dB. Correct? Now, one thing that you have to bear in mind is that this is nothing but, I mean, this, see, all this is only valid for weak nonlinearity, where A2 times A square is much smaller than A1 times A. but as you keep increasing the input amplitude, it is not necessary that I mean, at least if you do the math here, yeah. So, I mean, if you go on increasing A2 times A square can potentially become larger than A1A, I mean, just simply from the math, right. But at such large amplitudes, it will typically happen that the amplifier, which is weakly nonlinear only over a certain range of input amplitude, has now been pushed into a strongly nonlinear region, in which case none of these approximations basically work. So, in a practical amplifier, you shouldn't expect that this curve keeps going up and up and up, right. It will kind of do saturate like this, right. And likewise with the fundamental also. Just because it says A1A doesn't mean that you can put 100 volts into a small amplifier and expect the output to be 10 times 100, right. Okay. So, so these are basically regions where weak nonlinearity is no longer valid. All right. Now, let us say you had two amplifiers with the same gain. So, log input amplitude and this is log output amplitude, right. And you had one amplifier whose when I plotted the second order intermod power, you had something like this, and you had amplifier A and you had amplifier B. Which of these amplifiers is more linear? Amp B is more linear because even though both of them have the same fundamental output amplitude, the second order, the intermod distortion is lower for amplifier B. So, one way to quantify the linearity of an amplifier is the following, is to observe that if I produce this line or extrapolate this line, at some point it will eventually intersects the fundamental curve, and that happens when A1A becomes equal to, so at this point of intersection A1A must be equal to, or let me call this A1A star must be equal to A2 A star square. So, this A star on a log scale. So, A star therefore is equal to A1 by A2. Okay. So, A star is A1 by A2 and that therefore gives you, I mean if the amplifier is perfectly linear, what comment can you make about A star?
A star should be like infinity.
Should be infinity, right? Okay. So, the more linear the amplifier is, the higher the A star will be, right. a couple of things. So, I can see amplifier B, which is more linear, basically will these two curves will intersect at, right. Yeah. So, this is what is called the input referred second order intercept point. All right. Why does it make sense to call this input referred? Well, we are this is the x axis. The x axis is the amplitude of the input, right. Intercept point, well, when the intermodulation curve intercepts or touches the fundamental curve, the line is when at that point, and of second order because we are talking about IM2, right. So, this is often called also IIP2, right. Input referred intercept point, okay, IIP2 for second order, right. And so, this IIP2 therefore is basically it is an imaginary point. It does not mean that it does not mean that you can apply A star and at that point the second harmonic will be the same. I mean the second order intermodulation will be the same as the fundamental, correct. So, this is a problem. I mean this is something that we borne in mind, and so that is because these are generated from extrapolated curves, right. So, these are all extrapolations. In fact, the same thing holds for the fundamental also. So, all these are extrapolated curves or extrapolated lines, I would say. Okay. And so, they are basically IIP2 is a metric that quantifies the degree of non-linearity. Right. In a perfectly linear amplifier, IIP2 is infinity, right. And since both IIP2 and the second order intermodulation and is coming because of A2, and likewise the second order harmonic distortion is also coming because of A2, right. Basically there is a there is a relationship between the two of them. So, let us so if the input has an amplitude A, then the HD2 is A1 capital A by A2 capital A by A1, right, as you can see from our earlier analysis. So, I think right. Okay. If you have two input tones, with amplitude A each, IM2 is nothing but, remember IM2 is the ratio of the intermod tone to the amplitude of any one of those tones, the input tones, right. I mean one of the input frequencies, I mean we have to take the ratio with respect to the output amplitude. So, IM2 as we can see is nothing but A2 A square by A2 A square by A1A, which is A2A by A1, right. And so, under these situations we see that H IM2 is basically twice HD2 when they are all expressed as numbers and not in log scale, right. Otherwise, in dB, IM2 is HD2 plus 60. Okay. All right. So, so when does I mean in a practical amplifier, I mean in a practical system, where are examples where second order nonlinearity can be very problematic. An example is again an RF receiver chain. So, let us say this is the front end amplifier, this is the antenna, and this goes into the first amplifier, which is supposedly linear, right. So, I mean if you have two very large tones outside the signal band, what they can basically cause they can intermodulate to baseband, and then that DC offset can potentially go and change the bias point or the operating point of the device in the amplifier, right. Of course, it is also entirely possible that if you put two large tones, the amplifier gets pushed out of its weakly nonlinear region and can get saturated, right. So, so large inputs can have all sorts of problems, right. And so, let us say we have a small desired signal here and two large out of band interferers, right. So, this is FLO and this is F1 and this is F2, correct. So, how will the receiver work? Well, let us assume that the amplifier does not saturate. The next thing is that you have some kind of mixing operation, right. And so, this is what is called a direct conversion receiver. So, you mix the output of the amplifier with both sine and cosine to convert them to baseband, and then you are supposed to have a filter whose job is to eliminate everything other than the desired channel, let us say, right. So, the desired channel is basically a small signal which is sitting here, and then because you have multiplied the FLO with FLO. So, you have baseband to baseband, but then you have these two large signals here, right, and these two can intermodulate using through second order nonlinearity of the filter, remember the filter is made with active elements, right, and active elements are fundamentally nonlinear. You do your best to make them as linear as possible, but if you have two large signals, for instance, these two will through second and through IM2 will basically can either cause if these are two very closely spaced tones, they will basically cause something here which can be confused with your desired signal, right. Okay. So, that is what you need to be aware of with regard to second order distortion. Fortunately, in most electronic systems today, there is a fairly straightforward way of eliminating or reducing second order distortion significantly, and that is through the following within quotes trick, if you will. So, we know that this is let us say you have an amplifier with A1 Vi plus A2 Vi square plus A3 Vi cube and so on, right. And as I said, the higher order terms are usually negligible in the region of interest. Now, let us say we took another identical amplifier. So, both of them are identical and you apply minus Vi here. So, this will be minus A1 Vi plus A2 Vi square minus A3 Vi cube and so on, all right. So, if you look at the difference between the two inputs, it is 2 Vi, and the difference between the two outputs is 2 A1 Vi plus 2 A3 Vi cube and so on, right. So, this is what is called differential operation. Okay. And this eliminates all even order distortion. Okay. So, you have to only worry now about odd order distortion, right, of which is the most dominant one? Yeah, the third order distortion is the third order nonlinearity is the dominant component of nonlinearity in many practical circuits which all operate differentially, all right. So, in the next class we will learn about third order nonlinearity. Okay, and these are all at this point we are all dealing with circuits without memory. Once we have memory, we will have to figure something else out, and we will do that as we go along.